What is FEA? Excuse me. What is adaptivity and why would you do it? Um, in a nutshell, let's talk about a couple of things here that we want to discuss in this lab. First of all, let's talk about results of FEA mode, finite element method, or FEA. Well, it depends on the mesh, how quality mesh is, because it's the mesh that captures the geometry. The mesh is a mathematical representation of the geometry, the CAD geometry that you have on your screen. Uh, it, it's also going to depend on the order and the type of elements you use and the order you use, whether they're draft quality or high quality. You know that you can have draft quality elements and high quality elements, if you remember from the beginning of the class, and we'll review this a little bit as well. There's also other phenomena that you can use that can affect the results, and that numerical errors, modeling errors, maybe even user error, and you have errors in your system and that sort of thing. Also, you have to understand what your goal is if you're going to understand activity and why to use it. What's our goal when you run a study? Is it just to get some numbers, just to get some pretty colors on your screen? Obviously not. We want to get results that are accurate. How do you define accuracy? How do you gauge that? There's a few different, a couple different parameters we can use based on theory. The most typical one that you'll see is a strain energy density, and we'll use that to gauge this. Oh, how do we achieve this? How do you achieve this strain energy density to a desirable value? Well, there's two ways. One, because it's a mesh, we can modify the mesh itself, because that's one of the things we said the results will depend on. We can modify that mesh. Or two, we can change the order of the elements. If you talk about the order of elements, look at number two, the type and order of elements used will affect the results. If we modify or refine the mesh, that's called H additivity. If we modify the order of the elements used in the mesh, that's called P additivity. Take a look at the mesh, the order of the elements themselves. Just a little review here. If you see that you have your first order elements here, this is a first order tetrahedral shape. SOLIDWORKS uses tetrahedral elements for solids. The black one here, the black outline, shows the undeformed shape, the undeformed element before you apply your loading on your part. When you do, you see that the part does deform, the elements deform, and you'll notice that the first order, the edges of the element do not bend at all. That's because there's only 4 nodes, and each node is at the corners. So the corners deform, but the edges don't. It's only because there's 4 nodes, right? And that's going to limit your accuracy depending on how much your part is deforming. Just to recap again, 3 solid elements have 3 degrees of freedom. So at each node, so if there's 4 nodes, 3 degrees of freedom, this element has 12 degrees of freedom. First order elements are also called draft quality. Second order elements here, you'll see that they have an extra node here in the middle, and the extra node will allow for extra deflection on your part. That deflection that allows for the edge, that gives you greater accuracy when it comes to calculating the deflection of your whole part. So in other words, it increases the order, increases the power of each element, and you get better, more accurate results. Now, second order elements have, instead of 4 nodes, they have 10 nodes, because now they have an extra node in between the edges there, and that's what allows it to bend. Now obviously you can see that you went from 12 degrees of freedom to 30 degrees of freedom. Now that's going to increase your calculation time, but it's also going to give you much more accurate results. Second order elements are also called high quality elements. That's just a recap, and maybe I'll pull up the software and show you that in a second. Let's take a little bit further about look a little bit deeper into H and P additivity elements. H adaptive is called H because if you take a tetrahedral element here, look at this image, and circumscribe it in a circle, the diameter is what's called the H. That H, we call it H adaptive because it adapts that H based on where your model needs it. Now this is a mesh of a regular model. This is a mesh of the same model after running through an H adaptive process. Notice that down here in these areas where the geometry gets a little more complicated, a lot more elements are added, and that's done by making the elements there smaller, and therefore we can fit more of them, making the H smaller, hence H adaptive. P adaptive increases the polynomial of elements. So from first order goes into second order, on the third, on the fourth, on the fifth, and so forth. Hence the P. A good analogy to think about this is think about an engine designer. And if you're wanting to increase the power of the output power of a car, there's really two ways you can go about that. One, you can increase the number of cylinders, so go from a V6 to a V8 to V12 and so forth. Or you can increase the size of the cylinders, so from a 2 liter to a 2.6 liter to a 3 liter and so forth. Increasing the size of increasing the number of cylinders is analogous to H adaptive. Right? So where you go to V6, V8, V10, well, that's increasing the number of cylinders, that's increasing the number of elements, and that's how you gain more power. P adaptive, you'll gain more power. That'd be analogous to increasing the size of a cylinder. Larger cylinder is analogous to a higher order in the elements, so more powerful elements. Let's look at something here. If I take a look at this mesh here, show you this mesh. For the advanced options, you see that you have the option to go to a draft quality. By default, SolidWorks meshes second order polynomials, second order elements. It's when you select to have first order elements that you can select to have second order elements. Also notice that in that option, it only gives the option to go from second order to first order. To go to the higher orders, you need to use a P adaptive to the higher orders, and it only goes up to 5. Looking at these here, let's take a look at the P adaptive. Go to the adaptive tab. You'll notice that you can get to set when the P adaptive stops when the total strain energy, and we can set other parameters, but we'll go to total strain energy here, and you can set the percent change for the total strain energy. It's talking about total strain energy from node to node of your elements. You set your starting P order. You set your maximum P order. The maximum P order in all analysis is 5. In all of FEA is 5. Really depend, no matter regardless of the tool you use. And then you set the number of loops. Number of loops whether it reaches the order first or it gets number of loops first, whichever one is reached first is when the study will stop. So keep running and running and running and running. It'll run through all 4 loops, or it'll run until it gets to 5 polynomials, looking to get a strain energy of less than 1%. And just to show you the P adaptive here, the H adaptive, sorry. You set your target accuracy, and then you set your maximum number of loops. And so what it does is it will go through a number of loops, and if it reaches a number of loops, it reaches that high accuracy, it'll let you know. If it goes through all the loops without reaching the accuracy, it will also let you know that you get that, and you'll get that message when you got it.